All right, let's take a look at this particular series here. So we see the series is pretty basic, it's pretty straightforward. We see that our a sub n is simply just going to be the term number itself. In other words, when we are looking at the first term is 1, the second term is 2, the third term is 3, and so on. And we can find the sum of this series pretty easily, recognizing that it's an arithmetic series. So just using the sum formula for the arithmetic series, we can see that it would be n times the quantity of n plus 1 over 2. So let's actually look at the sum and let's kind of test that sum formula out and just make sure that it works. Well, what is the sum of the first term? The sum of the first term is just 1. That makes sense, right? And if I check my formula out there, I go 1 times 1 plus 1 over 2, and that does indeed give me 1. Now, what about the sum of the first two terms? Well, 1 plus 2, that's equal to 3. And just to, again, check to make sure that our sum formula works out, it looks like we would have our n value being 2, so 2 times 2 plus 1 over 2. That does indeed give me 3. Let's try that one more time. Let's try s sub 3. So 1 plus 2 plus 3, that's equal to 6. And again, let's checking our formula, 3 plus 1 over 2. And yeah, that does indeed give me 6. So it seems like the formula is valid, but the question is the formula always valid? And we can't assume that it is. So we are actually going to prove that this formula works, that this sum formula works, using a process called mathematical induction. And it proves this a number of different kind of approaches. A lot of our background is familiarity with proof by deduction, using truth or facts that we can then use to establish a next line of reasoning. But with induction, the idea is that we're using something that must be true about a first case, and then if we can show that it works for the next case, we can then make a conclusion about what it must do about following cases. So the principle of mathematical induction is written right here, and it says the following. It says if P1 is true, if the statement is true for the first term, and we can make some statement about the truth of P sub k, meaning for some positive integer, and it implies the truth for the next positive integer term, then it must be true for all positive integers n. So I want to actually go ahead and just do a mathematical induction proof here for the formula that we just discussed. And there is a little bit of a typo here, I apologize. This needs to be changed to I, just so we're staying consistent with what we said earlier. So this should just be I. So again, so let's look at this, and I'm going to leave those steps up there for the first part. So first, we want to say if, step 1, if P sub 1 is true, in other words, when n is equal to 1, then the sum of the first term is equal to 1 times 1 plus 1 over 2, and that is equal to 1. So we've just shown that when n is equal to 1, it does work for the first term. Next, we want to assume that s sub k will work. In other words, that it's going to work for some positive integer k, that this is true. Since it worked for the first positive integer term number, it's got to work for a positive integer term number. Well, if that's true, then we can make the following follow-up statement. Then, if it works for s sub k, then it must work for s sub k plus 1. In other words, this entire series that we just had, so let me actually highlight this in a color here. This entire s sub k, let me make that in blue, okay? So it's got to then work for the next s sub k plus the next term, a sub k plus 1. So let me write that, a sub k plus 1. This is just our way of saying that the sum of k plus 1, s sub k plus 1, has got to be the sum of k terms plus the next term. So we would then say s sub k plus 1 is equal to, and let's just substitute in what we said s sub k was. It's k times k plus 1 over 2. And what was the next term in our series? Well, we would say it's 2 times, or excuse me, k plus 1. Okay, so if k just represents the current term, k plus 1 is the next term. Now, in order for me to add these two fractions, I want to make sure that I have the same denominator. So I'm just going to go ahead and write this, all of that over 2. Now let's clean that up a little bit. So s sub k plus 1 is equal to k plus 1, and let's see here. We can say, well, I notice that there's a common factor of k plus 1 in both of these terms. So let's actually write k plus 1, factor that out, and what's left over is k plus 2, all of that over 2. Now, I'm going to pause here because I want us to make sure that we understand what we're trying to do. We're trying to show that s sub k plus 1, that it works, that we are getting this same structure. We want s sub k plus 1 to show that when we substitute k plus 1 in for n, that this formula is true. When n is equal to k plus 1, we want this formula to be true. So we want what we have written so far to look like n times n plus 1 over 2. Well, we're pretty close. And so the only thing that we would just really need to adjust here is to say the following. K plus 1, so n is equal to k plus 1. So let me kind of just match this up as I go along. So n is equal to k plus 1, so there's that. Next color, n plus 1 has to then be k plus 1 plus 1. There's our n plus 1. And all of this has to be over 2. I'm just kind of do a color for that. That has to be over 2. So what we've just shown is that, hey, it worked when n is equal to 1, so it worked for our first term. So we're going to assume that it works for a positive integer. And since it works for a positive integer, it's got to work for the next positive integer, which is the proof part. That's what we've shown. So now we can make our concluding statement. We can say, therefore, when n is equal to k plus 1, s sub n is equal to n times n plus 1, so our formula that we were trying to prove, and by mathematical induction, the formula is valid for all positive integers or integer values n. Okay, and so you don't really have to box this, but that's what I'm going to box as kind of my concluding statement. That's what we're looking for. Okay. Now, since this is a proof, it's really important that when you are writing out this proof that you are showing all of your steps here, right? We want to make sure we write both in if statements and show the proof. So for all of our mathematical induction problems, what we're ultimately trying to show is that this formula that we're setting out to prove from the get-go, works when n is equal to k plus 1. And that can't work unless we have shown these statements here to be true. Okay, so I encourage you to try this next problem on your own. Go ahead and try this, and you can go ahead and check my proof that I have uploaded to Google Classroom.